with that when then we want to play with vectors similarities. So what we need to do in this model that we now are going to dig into, which is the one behind ChatGPT and behind AlphaFold also. So if we understand this, we are like halfway to understand a lot of stuff. So this transformer works by first of all taking your tokens and embedding them in some space just through a linear combination. So this is the embedded matrix. We just have, so the token is the size of your vocabulary, V. This matrix is just random weights, needs to be learned, but these live in a real world of size, vocabulary size times D. This D is fixed in the model. So from now on, after we embed our input, which will have actually size, this is a token. The token after this operation will be of the measurement. You just take a linear combination that we know now, weighting your token features with some weights, okay? So it's a projection in a d-dimensional space. Each token will become a vector of d dimensions. This is really needed because this is the true input of your model. Actually, this is not really the end of the story, because I told you that transformers work with the ordered sequence of tokens, and but in the end, the network itself, the operation it's making, doesn't really have an idea of the order. So we need to inject this. We need to inject it at the beginning through a positional encoding. Positional encoding is important, but it can be done in very many ways, and it can be even learned by the network. So same usual game. You have some weights that are learned because they will be specific of each token. Each token has a position that's going to be important, and the network is going to learn the encoding. That's the typical way. But what I'm showing here is a fixed, is a sinusoidal way of doing this encoding. And why is that used? Because it gives you like unique values for your positions, and also it preserves kind of like it's not preserved, it's like it gets larger, but you have a sense of the relative distance between the tokens in this way. This is fixed. You just assign real numbers that will correspond to your position. Okay, so what you do, you sum your tokenized, linearly projected on a d-dimensional space token, and your positional encoding, which is of course in a d-dimensional space as well. Okay, from now on, our input will live in a d-dimensional space. Of course, here is one token. For the full sentence, the space is d times L, where L is the length of the sequence that you have. Of course, I mean, the operation that we're going to see, they work on each token, so it's kind of easier to focus on the token. Okay. And now, what is going on in the network? So why can this network learn from the context? So typical models that were working on sequential data, they used to work with the first token, learn something, carry it on the second token, learn something on the second token. So like literally mathematically add the information from the first token to the second one, and so on. This is very inefficient because you need to wait for the first token to be processed, and also the network is just going to see what's behind the token. So the trick with transformers is that with the attention mechanism that I'm explaining here, each token will will process simultaneously all the others in the sentence. By training, it will learn how much attention should give to each other token in the sentence. So how does it work? This is your input, number of tokens, d-dimensional. Okay? We've done the tokenization, we've done the positional encoding, correct. We introduce three matrices, Q, K, and T. Let's focus on these two first. These are conventionally called query and keys. Why? Because it's like they are, again, made of weights that needs to be learned. So you can call them whatever you want. It's just to give you the feeling that you are querying your token against the keys tokens. That's why they're called this way. But it's just a convention. What you do is a linear projection of your input, so you take each token and you project it in a dq dimensional space through a linear combination, which is 0. Nothing particularly hard here. You do it on another matrix, that is the keys. And you do it also on this other matrix, which is the values. But now, what is going to happen is that you multiply your Q and K together. Okay? You see that here they have the same dimension, dq, dq. So once you make this matrix multiplication, you are basically compressing the dq dimension. You are doing it on the dq dimension. So what you're left with is an n times n matrix. Okay? This is an n. You just multiply it and you get with this matrix, you arrive with this matrix. So this is the attention matrix, basically. Well, it needs a little step more because these are basically numbers that can be on any scale. There is no restriction on what this number should be. So we need the softmax operation. So just you go on a line of this matrix, which is one token looking at the other tokens. Yeah. N is the number of tokens, no? Okay. So you have an n times n, just like a contact map. If you imagine that your input was a sequence, this is the dimension of a contact map. So it's not a horrible object. It's handleable, and but it can have any number in it. We want them to be between 0 and 1 because, yes, it's they're much more interpretable this way, and they give you like a probability of looking at another token interpretation. So what we do is a simple mathematical operation, which is this. I guess that physicists have seen it somehow. It's probabilizing your input, the row of the matrix. This will give you a number that is between 0 and 1. Exactly. So, in the end, what we do, we take the attention matrix and we project on the value. Sorry, this I forgot to say. This is called value, still conventional. On the value 1. There are a lot of weights here in these linear combinations that needs to be learned during training. But the way this works, it's like forcing for each token, forcing the network to put much more weights on the tokens that are important to understand himself. This is going to be maybe more clear in a second when I tell you what the loss of this is, which is connected to the game that we play. Okay, one thing to say is, if you see here, there's dv dimension. I told you that the dimension in the transformer, like the representation size in the hidden layers, it's fixed to d. So why do we have dv here? Because you can do this process simultaneously in parallel, sometimes. It's called multi-head attention. So not just once, several times. So you left some flexibility to learn different types of correlations within the token. This is very helpful. So in the end, dv equals d divided number of heads. Why? Because then you take each heads that you process independently, you concatenate and take a linear combination. So in the end, the dimension will be d. Okay? I know this sounds a bit messy, but now I'll tell you what the loss is. So, of course, in any machine learning or deep learning model, you cannot understand what the weights should be, even for a linear regression, if you don't know what's the task, what's the network doing. Because I told you in that propagation, these weights are going to be adjusted to minimize the loss. So that's crucial. You cannot fully understand this just from this picture, right? We need to talk about the loss, which is, maybe I tell you, yeah, sorry, I skipped one because I think it's important to say this now. What is the loss of this project, of this problem? It's a mask language model loss. So this is a model that is called self-supervised itself. It works a little bit differently from the, if you remember, the autoencoder that was just comparing the input and the output. Here, the game is to mask some words, exactly as we did in the game we played. You mask some words of the input, certain random fraction. This is a model that is doing exactly this. It's called BERT in text. It's just randomly masking some tokens. The difference with GPT, so the model is exactly the same, but GPT will mask just the future words in your sentence. So it's a conditional masking. It's a little bit different. Here you have just a little simpler. You take your input, you randomly mask a fixed percentage of your tokens, typically 15%. And then the usual friend percentage. So how much error am I doing in guessing the value of the masked token? So you ask the network to reconstruct the masked tokens. That's the goal. The trick here is that while doing so, the network is seeing the others. The others are completely available, are not masked. So in the end, it will learn the masked values by looking at the context. Then, okay, that is also doing, that is for language, is also doing the next sample prediction task, which is more like a classification, whether two sentences are consecutive or not, but I don't want to focus too much on this because this mechanism, so the masked language model loss of BERT is what's actually used for protein language models. Now I just go back because I don't remember what I wanted to say here. Yeah, these are to give you just details. You should put it from the bottom to the top. And so you have embedding, you have this multi-head attention that I just explained, that it's just a black box here. And then you have just a couple of things that are important, and in particular this one. So what you're doing here, beyond normalizing, which I mean it's a scaling, it's a standard scaling, it's a score scaling, whatever you want to call it, it's simply You take the representations at this stage, you take the average, you subtract the average, and you divide by the mean, by the standard deviation. It's, let's say, useful for gradients, not to let your values explode somewhere, because they have the freedom to be whatever they want. So we need this type of tricks, like normalizing the values. But the key here is this add. It's very important because you are actually adding at each layer. You have an input of your layer, and the beginning is the input itself, okay? But then at the second layer, the input of the second layer will be the output of the first layer. You agree with this? So this should be added to the representation that you produce after the multi-layer attention. And this is kind of to keep track of what you were before the processing. It's called residual connection, and it's kind of important for the tokens to, let's say, let the information flow smoothly. And not to forget what it was, not to forget too much, okay? But of course, this is the key point in this model. Okay, last one on text. Natalia, do you know when I have to stop? Just tell me, then we keep. What time is it? Sorry? 50, so 10 minutes or something. Okay, maybe we can stop even before processing language models, and then we go back to it in the afternoon. And then we move to the lab.
Okay.
Okay. So first, transformer model. So to be completely precise, the transformer is an encoder-decoder model. The first one that was used is, you know what an encoder and decoder are, more or less right now. It was used for translation. So you need a decoder to map it to another vocabulary. The GPT-1, well, let's go to the back first. This is the encoder only. If you see, it's exactly just the encoder of the transformer. GPT is a decoder only, but it has exact same structure as the encoder. In the transformer, these are basically the same. But why is a decoder? Because I told you, it's the way you mask your input. You, at each epoch, you unmask one word in your sentence. And so what you're trying to minimize is a conditional loss. So basically you mask the future of your sentence and demask it at each epoch. So what you are looking at is the context before the word you are processing and try to predict the future, basically. This is not just prediction, it's generation in the end, because the model is guessing it and out of a distribution of words, basically. And you see that it's generative, no, in practice. This one is not generative, it's just encoding your, let's say, information that the model has learned into a vector. And I hope to convince you that these are like rich of information vectors. Maybe we can.
We have 7 minutes.
Okay. So, protein language models, they work exactly as BERT. The tokenization, of course, is going to be different from the one from text. It's not text, it's a protein. And it's kind of easy, the tokenization, no? If you think it's like natural. Each amino acid can be a token, I don't need to think about it too much. So at some point, after the success of these models that I just explained to you, what happened? So maybe one thing I didn't say, is it clear so why the attention mechanism coupled with a masked language model loss is learning the context. So it's doing some operation that basically it's putting in relation one token with all the others. And so if you mask some of the tokens, the arrangement of the weights during training will be to maximize the information that comes from the other tokens that will let it guess its identity. Okay. Okay. The operations are exactly those. You just change the input. And of course, I mean, it's very natural to do this, so people started to think that we could use these transformers for proteins, and they were right. So you are masking your amino acids, some of them, and during training, ask the network to reconstruct them. So the first people doing this, they, of course, at the beginning, they were like trying to analyze these representations that you get. This is an encoder, you get some vectors in dimension D. No, we have seen that. These are your embeddings, your representations. And yeah, so we want to know what information is stored there. It's kind of hard to see. The dimension is typically 1000 for a protein language model, so it's not so easy to understand how the network has stored information, biological information there. So what they did is a simple thing. They clustered the representation at the token level. You see here you have the amino acids, right? So what they're doing, they're taking a bunch of sequences, they are processing them with the model, not training here, just forward pass, processing them, producing these representations, and then you can ask, okay, let's take each token independently from all the proteins, and let's see if they group together somehow. Of course, you see that the same amino acids group together, but you also see, well, of course, it's not just for granted, let's say, it means the network has learned something, but maybe, let's say, it can be expected. But you also see the grouping in the famous classes I told you about. So you have hydrophobics, charged, and we've seen that in a multiple sequence alignment, well, let's see, in evolution, they can be used by evolution to do substitutions and still preserve the function. So they share properties, biochemical properties that are important, and so they cannot behave similarly. And we see that they group at the representation level. Very good. This is telling you there is some biological information in these representations. If you play this game with pure letters, no way you're going to get something like this. You agree with me, right? I mean, letters are letters. Maybe amino acid A is hydrophobic, B is hydrophobic, but they're not going to group together. If there is no information about hydrophobicity, it means here there is some, okay? No, maybe I'll stop here. Yeah. Okay. See you later, and we'll go just a little bit on and then exercise. So just the exercise of today will be, because I think you can already understand this. We have the sequence representation. We're going to use these representations in place of the sequence. Remember the exercise of yesterday, classifying beta secondary structure patterns, full beta, full alpha, starting from the sequence with a logistic regression. We're going to start from the embeddings with a logistic regression. In theory, it should improve. We need to check that. No, it should. The key point I'm going to tell you later is that it's going to be better.